No. Okay, come. Let me tell you guys what we're gonna do today and next 2 weeks. All right. So today I'm gonna do a March, so-called March common test revision now, because you guys have. I know you guys don't have a March common test. Okay, but some schools have. And the idea is that generally we should use this as a revision now. Okay, might as well. Okay, so before we move on to the next chapter, which is carbonyl compounds, okay, we do a little bit of revision first for some of the more crucial topics we have gone through since promos. Yeah, okay, so some of the recent organic topics are inside. Okay, there's some acid-based stuff inside as well. Okay, so we will do both today. Okay, so I ask you, do you want to do acid-based first or you want to do organic first? You want to choose? Acid-based first or organic first? Okay, let me help you choose now. Okay, we probably want to do organic first. Okay, later then we try a bit of an acid-based question. Okay, so we start with a very simple question today. All right, so I want to try a couple of questions. We can't finish everything. Okay, so I'm gonna time you guys for every part that I'm gonna give you. Okay, so for question 3, I just need you guys to try part A. Right, part A is made up of 4 parts. Okay, and for these 4 parts, right, I think generally about 6 minutes is enough. Okay, I think 6 minutes more than enough actually, because some of the first few parts, right, very easy. Okay, so I want you all to try part A, all 4 parts. Okay, the crucial one is part 4 where you need to draw a mechanism. Okay, so I'm gonna time you guys starting now. Okay, you guys go and try 6 minutes. Okay. Hey, oh. Okay, we're doing question data. Okay. Nine questions now, so we're doing question 3A. It becomes about 6 to 7 minutes. If you have been working a cheat sheet for halogen derivatives, this portion here shouldn't be very challenging at all. Right? You have 2.5 minutes left. Okay, by now you should be at your mechanism. Right? They give you a bit more time, right? 1.5 more minutes to go. Give 4 more minutes. Okay, I'm sorry. All right, so I gave you guys about 7 minutes there, which is, I honestly feel this is a rough, pretty good estimate of these 4 questions. Okay, the general rule is this now, if you all still didn't know yet, right? Every mark is 1.5 minutes. So we have a total of 6 marks here, right? I should by right give you guys 9 minutes, but sometimes you shouldn't take it too hard, because some of the questions are definitely faster. Like for example, the nucleophiles definition. Okay. Now, I already told you guys that the nucleophile is electron rich. Okay, you guys also know that the nucleophile is electron rich, but that's not enough. Okay, for a definition question, I need more substance. Okay, so I need to see stuff like containing a lone pair of electrons. I think right until here, right, is honestly a very good answer already. Okay, if you tell me electron rich, which has a lone pair, good. Okay, the rest of the parts, right, is just what the answer key also provided. Okay, not to say that it's necessary also, because I feel that it's not necessary to the definition of the question. It does make it better, okay, but no lah, never mind. Okay, if you don't remember it so long like that, okay, can. So in order to be electron rich, you must have a lone pair. That's what we have always seen now. As long as you have a lone pair of electrons and a negative or even a negative charge, okay, it makes you a nucleophile. Anyways, okay, for the first three parts, right, I really think nothing here is very special. Okay, the second part is just a reagents and conditions. Sorry, that's the third part. Okay, the second part, right, is just a reaction. Okay, they tell you, right, you have one bromobutane and they add KCN in ethanol. In other words, ethanolic KCN and possibly some heat, right? Okay, I hope you realize this is a very simple nucleosubreactant. So this is your structure. That's pretty much it. Okay, now try not to draw a structural formula here. Okay, because as you can already see, this is one of those questions that already tell you guys to draw a skeletal formula. Okay, take note, right? Skeletal means everything is like the backbone is skeleton, but Cn doesn't need to be a skeletal formula. Okay, if you want to know how Cn in skeletal looks like, right? It looks something like this. Okay, so it looks a little bit odd because Cn is a triple bond with a nitrogen over here. And this is a linear shape. That's why it looks like a straight line. There's no bend in this case. Okay, but it doesn't matter. Okay, for skeletal formula, they also accept it if you put Cn. All okay so far? All right, then moving on to the last part, right? Honestly, this is very simple because you just need to change one bromobutane into one butyl amine, something like that. Right? This is just a nucleosubreaction. So honestly, all you need is ethanolic concentrated ammonia, and you heat it in a seal tube. Now, there's nothing much for me to discuss over here, right? All I can tell you is just go and do up your cheat sheet. Because when you do your cheat sheet, right, you're forcing yourself to look back at all the content first. Again, content is only like 30% of the cheat sheet. Okay, from whatever that I've told you guys and whatever you've been doing so far, it has to be filled with more questions. And the questions, like all these synthesis questions, right, will start to showcase whether you can actually remember all the appropriate reagents and conditions, depending on the question. Okay, there's nothing here very difficult at all, so I'm just going to move on already. Okay, I'm just going to show you guys the mechanism in part 4. If you need the cheat sheet for halogen derivatives, part 4 is the exact same mechanism as we did in class. Okay, so let's take a look, right? For part 4, you must first identify what's the reaction type. Because if they ask you to describe a mechanism, I need a name, right? Guys, what's the title of this mechanism? Okay, so I see some of you all right. Okay, you can't visualize, then you draw the entire structural formula. Take note, we don't have time for that in an exam. As you can already see, time is very tight. Okay, you guys never finished the mechanism in part 4. Okay, so can someone tell me what's this reaction over here? It's basically the reaction in part 3. What's this? Okay, anything to do with halogenoalkanes, RX is what reaction? It's just nucleophilic substitution, right? Okay, wait up. But for RX, do remember there are two different types of nucleophilic sub. Okay, this is purely a content question. There's nothing application based here. So all you need to tell me is in this question, is it SM1 or SM2? Any idea? Okay, so if you don't know this, right, that means your content is really not there. Okay, so please, okay, you must make sure that you know everything here. Okay, this is a primary halogenoalkane, and since the question never tell you any other properties, right, you can already assume it's SN2 nucleosub. If you tell me it's just nucleosub, also that one is wrong. You need to specify the name. Okay, so take note, right? Only your halogenoalkanes, you must specify SN1 or SN2. That's just how it works. And then from there, you just need to showcase everything you know about your SN2 mechanism really. Now, first of all, do you all remember that SN2, you need to draw your stereochemical formula? Okay, take note, right? I need to see this shape being shown in your diagram. Okay, this is the shape that needs to show, right? When you draw SN2 nucleosub, stereochemical formula, the bonds are generally facing the left, and then except for the halogen that's facing the right. Now, I know, right, I told you guys to draw skeletal. It's possible to draw skeletal here also. Okay, but we try not to. Okay, so this CH3, CH2, CH2. Okay, this carbon bonded to this carbon. Now, as for the others, right, okay, just put in the H's. So I basically converted this carbon in the middle into a stereochemical formula. Can you see that? So you must draw this version up. Because in SN2, there is a feature regarding its stereochemistry. But first of all, you are attacking with NH3 nucleophile. So I need to see the lone pair being shown. And this lone pair must attack this carbon here. So carbon has a partial positive, that's why it can be attacked. But guys, what must happen now? After the bond attacks, then, okay, you must break the bond, right? Because you have carbon here which forms a fifth bond, which is not possible, so you want to break the fifth bond. Okay, you're breaking and forming simultaneously in SN2. From here, you have a slow step, right? Hello. If you're doing fraction 3D, we don't finish in 3D. Fine, okay, so more problem. Okay, so after this, what do you need to draw? Okay, it's not intermediate, what's it called? Okay, good. Transition state. So what I need to see is the bond isn't really formed nor broken. So it looks something like that if you all remember. Okay, everything else we just need to copy inside. So look at the bond at the top, right? I'm just gonna fill this in. But can I ask you all, how about the solid and wedge bonds? Do I need to do anything to it? I did mention before. You need to flip it up. So now the solid bond is facing the left, dash bond is facing the right. Just now you can see that the configuration is opposite. So do something like this first. Is there any charge on the transition state? Okay, is there a charge? Okay, there's no charge over here because, right, overall the reaction is neutral. So here I also need to see a neutral transition state. Okay, and then from there, you just need to proceed to your last step, which is your fast step. This is where you can form the new bond with the nucleophile, and then you break the bond with Br to form Br minus. However, this is not finished yet because you still need to place everything rightwards. Okay, face all your bonds rightwards, something like that. That is the inversion of stereochemistry. So take note, these are all the properties that we have gone through before. We just need to reflect the same thing over here. Everything we've drawn before. Nothing new. Okay, and then from there, guys, is this the final answer? Is there anything missing in this reaction? Anything? Okay, I hope you all realize the nitrogen here has 4 bonds. A nitrogen cannot hold 4 bonds in a stable compound. And because of that, I need to see one of these NH being broken. What is eventually the answer? So there is actually one more step in this question where I need to correct the mechanism. Okay, I hope you realize the nitrogen here is a positive charge because here at the very start he's giving away electrons. I did tell you guys before, you lose electrons, you must have a positive charge. So you have a positive charge here, but before you draw any arrows, just go and draw the final product. Guys, what's the final product like? NH3 become NH2. You don't know how to draw the arrows yet, never mind. Just go and draw in the final product first. And by doing this, you have a better idea of how the arrows will move. What is the other product? Where did the other H go? Okay, it goes to PR to form HBr, right? Okay, so go and very quickly draw in the final arrows in this question. Okay, again, I didn't see any of you all manage to get this, again, which is a little bit worrying if I were to say so. Okay, luckily you all don't have much tests, but then again, this is not acceptable. Next week, we will be doing a mock test in either way. These are easy marks to get, C marks. Yes, need to write slow and fast. Okay, technically one step, right? Okay, so you can don't write the word fast. No. Must write slow. You know why? Because it's SN2 nucleosub, right? The reason why it's 2 is because it's an overall second order reaction. Overall second order kinetics, right? Means I have both the halogenal alkene and the nucleophile. So in order for this to follow the second order kinetics, it means the first step has to be the slow step because first order Rx, first order with the nucleophile as well. I don't know why your teacher marked it wrong. It is the slow step. Okay, it might make sense if you don't write the fast step because overall it is a one-step reaction. Okay, but you definitely need to write slow. Okay, if your teacher marked it wrong, I really don't know what to say. Okay, I can confidently say she's wrong. Okay, it's definitely a slow step because the kinetics aspect of SN2 and SN1 is very important. This is how you show the kinetics. Okay, and most you just don't write slow in front of her. Okay, but then in the exam must write. Okay, so how do you draw the arrows here? I don't think it's very tough. Okay, here you can see the H is gone to PR. PR is PR minus, so you must show me the lone pair attacking the H, and then the bond must break, and the bond break already, the electrons go back to N. That right there are the arrows. And that's finished. That's it. Okay, there's nothing else for me to comment on this because everything I've already commented in class. Okay, the purpose of this question is just to warm you guys up only. You shouldn't take this long. Okay, now we're going to proceed over to the next part of this question. Let's finish this up. Again, more content, no application yet. Okay, so go over to part B. I'll give you guys about 6 minutes to finish these 3 questions. Not tough at all also. Okay, I've taught you guys everything over here in fact. Okay, so anyways, 6 minutes. Okay, we start now. Just finish up part B. Yeah, chop chop. Anytime these kind of questions are questions that the moment you see, you already know what to write. Okay. Okay, we have 3 minutes left. Eight, 2 minutes. Should be on your last question by now. Okay, one final minute. Give you another 30 more seconds. Yeah. Okay, anyways, okay, ask me in a bit. All right, we took 7 minutes to cover this, which is fine. Okay, why am I able to give you all 1 more minute? It's because once again, go and allocate the time yourself. 5 marks, maximum 7.5 minutes because you times 5. Now, there's sometimes, right, guys, there's a merit to giving yourself less time. Okay, for content questions like this, right, I really think you guys can actually hit 6 minutes. Okay, because by right, you should have 7.5 minutes, right? Let's just say you only take 6 minutes. Okay, then where do these 1.5 minutes go? 1.5 minutes is a 1 mark question then. Meaning to say you can channel this time to some of the other 1 mark questions. Okay, eventually, right, as you keep cutting time for content questions, you will have more time for application questions. And then that's how you manage your time. That's how you never ever have not enough time in the exam. Okay? But anyways, okay, if you look at part 1, right, I think we've covered this a few times. Okay, there's a reason why this structure cannot react because you can see the Cl is bonded to a double bond. Okay, if you can't see the structure, okay, that's how it looks like over here. So this structure, right, you can clearly see Cl is bonded directly to a double bonded carbon. I already told you guys why this doesn't work. Okay, if this guy doesn't undergo nucleus up, that means this bond is very strong. A strong bond, the only concept you can think of is partial double bond character. It has the strength of a double bond even though it's just a single bond. All that is because of p orbital overlaps and delocalization. Honestly, right, these are the keywords. You need everything. You may be asking why you need to write so much for 1 mark. It's not about how much you write. It's about how easy it is to get this mark. It's very easy to get this mark. Yes. Sorry? Oh, sorry. Okay, not benzene, double bond. Okay, but some benzene works as well. It's a more common scenario. My bad. Okay, it delocalizes into the double bond due to p orbital overlaps. Okay, cut it short. And that's how you explain partial double bond character from now on. Right? Not very tough. Moving on to the second question, they gave 2 marks for part 2, which is very generous, okay, because it's a very easy concept. Guys, what's the concept over here in part 2? If they are asking for time taken, this is a what concept? It's a rate concept, right? It's a kinetics concept. So can someone tell me how much time you need to take for this guy to form a BBT? Okay, you have to give a value, all right? So does it have to be longer or shorter than chlorine? Way shorter. Okay, so it doesn't matter if you tell me 200 seconds, 300, or even 400. Okay, just make sure it is below 460 seconds. I'll just put 200 here. Okay, your explanation is how do you explain rate when it comes to Rx, nucleus up? What is it affected by? Okay, this is a very simple question. Take note, this is only 1 page in the notes. It's only 1 page because it is a chem bonding concept, bond strength. Okay, bond strength is all about your effectiveness of orbital overlaps. If the orbitals overlap, more is a stronger bond. That's all you need to talk about here. And the key points are very simple. First of all, just tell me that Br has a larger size or larger atomic radius. Larger atoms overlap better or worse? Okay, worse. So there's less effective orbital overlap, resulting in what? Go straight into strength really. If the orbitals overlap less, that means the CBr bond is weaker than the CCl bond, which requires less energy to overcome. Okay, it's about energy here because you do need to break the bond over a certain period of time. Less energy does mean that you are going to break it faster. As long as you have these keywords, I'm done already. So I'm going to construct a full sentence yourself. Okay, very simple answer. Let's just move on to part 3. Part 3 has a little bit more kinetics ideas, right, when it comes to SN1 and SN2. Okay, guys, in this question, right, when they say state the overall order, what's the answer here? What's the overall order of reaction when you switch to this compound? Okay, 1. Now, it's a very easy answer to get because in the previous part, when they ask you to refer to A part 4, they said that the order here is different. There's only 2 different orders for nucleosub, right? So 1 means it's a what kind of reaction? SN1. SN1, 1 means overall order is 1 already. Okay, and then you just need to justify why is it that this particular compound undergoes SN1 instead. How should we explain? How should we justify? Why? Okay, why is it that this particular compound undergoes SN1, whereas this particular compound undergoes SN2? This is whatever you have drawn just now on the right hand side. Now it undergoes SN1. Why? What are some of your basic assumptions? Okay, good. This is a tertiary halogenoid alkane. This is primary, right? Okay, but this is not really the main idea. What I want you guys to tell me is how will you argue this question? Okay, because you can argue in 2 ways. Okay, tertiary halogenoid alkane has a stable whatever. Okay, primary halogenoid alkane has its own reasons also. Okay, guys, how should we argue this question? There are 2 possible ways, or is both allowed? What should we be arguing for here? Why does this guy favor SN1? It's because his carbocation ion has to be what? Stable. Good. Okay, remember, if you want to argue anything SN1 related, it's about stability of carbocation ion. You do not tell me anything regarding steric hindrance. Steric hindrance is an SN2 concept. So in this question, you have identified that it is an SN1 favored reaction, meaning you must tell me that the carbocation ion is stable. Why is the carbocation ion stable? I'm sure you guys can identify that straight away. Perhaps let's just draw the carbocation ion. How to draw the carbocation ion? I feel that this is very simple. Just remove the halogen and place the carbon, place the positive charge on that carbon. Very simple, right? So what's the reason over here that this is stable? Okay, it has more electron donating alkyl groups, which will do what? What's the next point? More electron donating alkyl groups, which will disperse the positive charge to a larger extent. Okay, compared to a primary carbocation ion, that's for sure. Now, if you disperse the positive charge, that means your carbocation ion has to be. Okay, we touched this recently in alcohols and phenols. If the charge is smaller, it is more or less reactive. Less reactive. Less reactive items definitely more stable. So in this case, the carbocation ion of this guy is more stable. So it favors SN1. Take note, there are some ways you guys can get this question wrong. The first way is if you argue in terms of steric hindrance. That one has no relevance here because here is about SN1. Okay, very simple answer here with 3 bullet points. Tell me these 3 bullet points, you can get your 2 marks already, including you state that the overall order is what. That's it. Okay, any questions? Okay, very easy question. I pretty much expect you guys in the exam, right? This one you must get. Honestly, ideally full marks. It's definitely possible. Of course, I can allow for 1 or 2 marks of discrepancy lah. So out of the total of 11 marks, right, you get 9 or 10 is excellent already. But honestly, you can fight for 2 marks, 11 marks. Okay, nothing here is difficult. No application. Any questions? Okay, your school questions definitely going to be more difficult, okay, all of you included. Okay, we're going to try another question now. I don't think this question is hard also, but it's just good. Okay, so your turn to question 9. We're going to do this EJC question. We're going to finish this entire thing, but I tell you guys which parts to do first. Okay, it's not long, honestly. If you all take a look, this is not a long question at all. Okay, I want you all to do 9A, part 1 to part 3. We do segment by segment. It is how we train our time practice, our time management. Okay, eventually I'll start to ramp things up, right? I'll give you guys the entire question and then I'll time you all like 15 minutes straight up and do everything. Okay, now we do slowly first. Okay, for part 1 to 3, right? It's 5 marks. Okay, I will give you guys 7 minutes. Okay, definition questions. You guys probably know what order and half-life is. But you may not know like exactly word for word what the definition is, and it doesn't matter. Okay, you try to smoke something out first. Don't just leave it blank. Right? Who knows whatever you smoke out, right, can actually be the definition. Right? It might surprise you. Yeah.
Like, is it supposed to change from a dash to, I mean, from dash to like wet? Like the wedges?
Okay. I think this is the old version. I told you guys to draw one ourselves, right? All you need to do is to swap. I told you guys before, try to maintain consistency in the fonts. So I know sometimes the notes, right? Certain notes will have different like notations, but it's fine. All you need to do is this. If you started off like that, right? CH3 is solid, dash is H. When you swap the time, the solid will still be CH3, and then the dash will still be H. Whatever group that you assign will be there forever, so it's consistent. Yeah, just keep to that. I think that's a little bit easier. Yeah, the only thing you need to show is the swap of the position. That is the position. Yeah. Okay. Yep. For this one, right? Why don't have the charge? Sure. Why not have the charge? There's no charge because it's all about balancing equation. If here is neutral, here must be neutral, here must be neutral. The nucleophile is neutral, so everything's still neutral. There's no charge. That's it. Yeah. Here, right, you have a negative charge here. Because the bromine gain an electron. You forgot about the arrow here on the partial charges. But then over here, right, the nitrogen has a plus charge when neutralizing. So it must be neutral throughout. It's all about balancing of equations. Two minutes. Okay, part two, you do not know how to explain, move on first. Because part three is a mechanism. Easier to score your marks there. Okay. C6H5 is a yeah. Nothing else. There's nothing else in chemistry where you can have less hydrogens and carbons, except for benzene. Or if your molecule has a lot of double bonds, but we don't look into that. I'll give you guys another 30 more seconds, right? At least try to complete your mechanism. Okay, time's up. Okay, all right, so I want to go over a couple of things, okay, especially part two. You guys haven't touched kinetics in a while, so I want to bring back a bit of kinetics ideas because you never know, halogenic alkenes, they will infuse it with kinetics quite often, more often than you think. Okay, but anyways, definition question, right? How do you smoke it in the exam in case you forget? Half-life, there's nothing to smoke here. Half-life is the time taken to reach half, right, of the concentration. That's it. Okay, you just phrase it a bit nicely, then can already. Okay, take note, it's always concentration of reactant. Other than that, there's nothing for you to take note here. Okay, product, you don't measure half-life, it's just a reactant. Okay, for order of reaction, I'm sure every one of you know what order of reaction is and know what it means, but you do not know how to define it. Okay, and honestly, right, it is quite stupid when you look at the definition. Because order of reaction, right, is the power or let's say the coefficient of the reactant. Which one is it? Is the order the power to the reactant or the coefficient of the reactant in the equation? Okay, it's the power, right? Yeah, okay, don't write coefficient, that's wrong. Okay, so honestly, the definition is just this. The order reaction is the power to the concentration terms of a reactant in an experimentally determined rate equation. That's it. Yeah, okay, if you look at the thing like from a, if you look at the sentence, right, it's really not that useful. They're just telling you it's the power to the concentration terms in the rate equation. The only thing I need you to really include your answer, right, is the word experimentally determined. From the very start, when you first learn kinetics, we all know that your order of reaction cannot be derived mathematically or some other way, right? There is only one way to determine the order, which is to conduct experiments and interpret the data from that. So that's exactly what I'm doing right in this question. I have conducted a very specific experiment to try to determine the order of a reaction with respect to a certain reactant. That's the objective of these first two sentences. Okay, fine? Okay, the very first sentence they say, secondary halogenal alkanes can either go either primary or secondary. You should know that also. And because it is indeterminate, we have to conduct an experiment to really find out whether it's SN1 or SN2. So if you proceed over to part 2, right, okay, this is what this question is about. Part 2 is testing you on whether you understand your kinetics very well. Okay, come. Let's see first. You conducted this experiment, the halogenal alkane, obviously this is the nucleophile, right? Nucleosub. And then they measure the half-life, yes, sure. Okay, look at part 2. Although the half-life is constant, it cannot determine whether it's SN1 or SN2. Okay, first of all, guys, what does it mean when the half-life is constant? Now you look at this here. They say the half-life is constant at 277. Usually when this comes into play, right, what is the first thing that enters your head? Okay, first order, okay, again, that is not specific enough, right? Okay, so for now, we just know that there's something to do with first order, and order of reaction is generally tied to SN1 and SN2. Okay, so we're kind of there first. We form some very small little basic connection with the concept first. Okay, then you read the question again. Although half-life is constant, it cannot determine whether it's SN1 or SN2. So they're saying this, although it is a first order from the half-life constant fact, we can't actually determine whether it's overall first order or overall second order, right? Okay, so for now, maybe, right, if you want to really see what SN1 and SN2 is, maybe you write down a rate equation. Okay, tell me SN1, what's the rate equation? K times the Rx of the nucleophile. Rx. Whereas for SN2, its rate equals to K times Rx and the nucleophile. In this case, it's OH minus. Let me just put OH minus. Okay, you're gonna write them out first so you can see something more concrete. Okay, so they're saying, guys, if the half-life is constant, that means usually which one should, what will you expect, SN1 or SN2? SN1, right? Because 1 means overall first order, and half-life constant means first order. So that's what everyone thinks. But clearly that's not the case in this question. We can't do that. That's what they're saying here. We can't do that. Why? That's what they're trying to ask you. Can see that first? So establish what they want first. You understand what the examiner wants to test you on. Then come back to this experiment. Okay, maybe there's some flaw in the experiment. So we take a look. Okay, you look at the two reactants here. What do you notice? You have to notice something. Okay, good. Okay, do you all realize the concentration? Look at the concentration of each reactant. It's very specific. Is there something you notice? You say different concentration. Of course, it's different, right? Everyone can see it's different, but how different? Good. Okay, guys. This guy is not in excess, but in large excess. Now we try to understand again. What is the purpose of making something in large excess? Okay, I can show you guys this. Imagine we have A and we have B. These two guys are reactants. Okay, imagine this. The concentration of A, I times 2. Concentration of B, I times 2. Now, you end up calculating the rate times 4. Can I ask you, all right, is this conclusive? Can we determine the order with respect to A and B at the same time just from this one experiment? Guys, times 2 here times 4, right? Is there any possible order of reaction of A and B? Can someone tell me what are some possible orders? Okay, what are some possible orders of A and B? Any idea? Come on, kinetics. Okay, good. Okay, so first order, but is that the only conclusive answer? It can be what? It can be 2, 0 or 0, 2, right? Okay, so guys, what I'm trying to say is this. When you try to investigate two reactants at once, it is not conclusive. Makes sense? I mean, proven by this example here. So guys, we have to, if you can't investigate two, we investigate one at a time, right? But how do we investigate a reactant one at a time in order to find their order of reaction? What should we do? Exactly, guys. If you want to investigate one at a time, that means the other guy must be muted, right? You must block him. Make sense? Okay. How do you block him? I'm going to use the word mute. It's by using him in large excess. Okay, we slowly get to the terms. If you put this guy in large excess, that means his concentration is what? Relatively constant, or you can treat it as constant, right? If the concentration is relatively constant, does it affect the rate of the reaction? No. It doesn't affect the change in rate. Now, of course, it affects the rate because it might be first order, it might be second order, we don't know. Okay, but here, if it doesn't change much, that means the rate also doesn't change much, so it doesn't affect the change in rate. You can see that. Okay, don't use the word doesn't affect the rate. It's the change in rate. Okay, because it can be first order, it can actually be first order. That's 2 mole per dm cube will actually affect the rate. Okay, can? Now, if it don't affect the change in rate, that means this is what concept? Just now someone mentioned also. Okay, it is pseudo, doesn't affect, so it's what order? Doesn't affect, that means it is a pseudo 0 order reaction with respect to who? NaOH. Guys, can you see what's happening? NaOH is in large excess. You put in so much more, right? So that he doesn't change much. If he doesn't change much, that means the rate also doesn't change much. So if it doesn't affect the rate, right, that's a 0 order ideal. So, yeah, so pseudo 0 order with respect to NaOH. Now, I haven't really answered the question yet. I'm just recapping the idea of large excess with you guys. Making something in large excess means you have effectively muted this guy. You block this guy from affecting the rate. You can see that that's a pseudo 0 order. Now, when you mute this guy, then you can study who. Okay? It's like when you want to talk to 2 people, but one of them very annoying, then you mute him, right? You mute this guy so you can talk to the other person. Make sense? So we can only now study the order with respect to Rx. So go write this down. We are doing all this shit over here so we can study the order with respect to Rx. You can see this is an experimental technique. Study one at a time. I'll show you guys why you can't study 2 at a time. How do you study one at a time? You can't just remove that guy, ma. You need him to react. So you mute him. This is how you mute him. Okay? Mute him, study Rx. Okay, guys. So can you all tell me, with the fact that the half-life is constant, it is actually first order with respect to who? Okay, good. Now let's rewrite this. Okay? Since we have muted NaOH, the half-life constant means it's first order with respect to this guy, obviously. The guy is blocked already. Can you see that? So we'll write this down. Okay, it's not exactly first order, it's pseudo first order. Because, it's kind of a pseudo reaction. So it's pseudo first order with respect to Rx. Once again, we're talking about Rx. Can you see that so far? So I say what we have just gone through. This experiment, we can conclude that it is first order with respect to Rx. But why can't we still determine whether it's SN1 or SN2? Can you look at the 2 things that are written over here? First order with respect to Rx. Look carefully. What do you notice? Whether it's SN1 or SN2, both of them are first order with respect to Rx, right? Yeah, now how do you determine whether it's SN1 or SN2? That's the answer. Okay? Both of them are first order with respect to Rx. In other words, the answer is I never actually studied my OH minus order. That's why I don't know whether it's SN1 or SN2. Okay? Now, the phrasing of your answer, don't worry too much about it. I need you all to understand first. Anyone confused now? Okay, so this question, yes, we understood it is first order in respect to Rx, but no matter SN1 or SN2, it doesn't matter. Okay, we're still not conclusive. So you can write this as your answer. Okay, you can first tell me about the large excess stuff. Okay, concentration of NaOH is in large excess, which means reaction is pseudo zero order with respect to OH minus. Okay, this is whatever that we've learned so far. Okay, so what is pseudo zero order? The constant half-life in this experiment tells us what? The constant half-life tells us that the reaction is pseudo first order with respect to Rx. But you notice it doesn't tell us anything about NaOH. Okay, but does not tell us the order with respect to OH minus. And it's because of that that we can't determine whether it's SN1 or SN2. Okay, thus we cannot determine if it's SN1 or SN2. Something like that. Okay, it doesn't have to be very, very structured in your answer. As long as you kind of get the overall point across. Okay, now you may be asking again why they give 1 mark. Again, okay, this is one of those harder 1 marks to get. They could give 2 marks, but then more people will die. So which one would you prefer? Right? Okay, there's a reason why we make stuff in large excess, not for fun. Okay, it's so that we can study one at a time. Okay, sure, we study this guy. But in whatever case, SN1 or SN2, right, it doesn't matter. Right? Okay, then to really help you understand this better, right, how do you actually solve this problem? Okay, guys, how would you solve this problem? We don't just identify the problem and just leave it. Let's just then move on. Okay, no. How will you solve this idea? Okay, we want to study the order with respect to OH minus, right? What can we do? The first experiment, I use 2 mole per dm cube. The second experiment, how much can I use? The second experiment, why not I use 4 mole per dm cube, correct? Now what happened to the concentration here? I have effectively doubled the concentration, right? Now when you double the concentration, now let's study the initial rate. The rate over here, what happened? If the rate double, then what can you tell? Okay, it is first order in respect to OH minus. So then which one is it? SN1 or SN2? SN2, because it's first order. Now if you double the concentration to 4 mole per dm cube, and then the rate doesn't change, so it times 1, then what is it? 0 order in respect to OH minus means it is SN1, where there's no OH minus there. That's one way you can solve this problem. This is comparing initial rates. No, okay. Okay, good question, good question. Okay, see this. Okay, let me just repeat the question. You are saying large excess doesn't affect rate, right? But no, it doesn't affect the change in rate. You can see that? Overall, it still affects the rate. So let me show you what I'm saying here. Now, let's treat it as if it is actually first order. Rx, 0.05 moles. NaOH, 2 moles. Can you see that? Now, let's just say the rate is 10. Random number. Now, I can still put Rx as the same. Now, I can change this guy to 4. Is it still in large excess? Yes. Okay, but here it's not about whether it's large excess or not. Because if NaOH is first order, what is the rate here? 20. It is large excess, but here it's not about the change in rate. This is just the initial rate. Can you see that? Change in rate means because it's so much, right? This is what will happen. Okay, initial rate will be changed. Okay. But let's just say you're starting just one experiment, then you track the rate over time. Okay. Now let's just say after a while, this one drops to 0.025. Okay, 0.025 Rx. And here will drop by how much? Okay, you minus 0.025. Here must minus 0.025 also, right? Because it's 1-to-1 mole ratio. Can you see that? Okay, so here will be 1. What? Okay, 975. Yeah. Okay, so can you all see the concentration here doesn't change much. But here the concentration is literally like 50% smaller. So this is the change in rate. Does this gonna affect the rate that much? No, it doesn't. So it's the change in rate that is not a factor. Because it only goes down a small minimum amount. Can see what I mean here? You can change the rate entirely and it can still affect the rate if it's first order. But if you let the reaction go over time, right? When the Rx decreases, NaOH decreases by a certain amount, but in proportion is much smaller. So it doesn't, this 0.025 doesn't affect the rate much. But this 0.025 will affect the rate because it's such a large change. It's all about change here. That's why I highlighted the word change. Can you all see that in the bigger picture now? Okay. So perhaps maybe I wasn't clear at this change, but so you can use numbers to showcase this. Okay, can? Yeah, no? Okay, so that I spent quite a great deal of time on this, right? Okay, because I feel that kinetics has this problem when you all look at pseudo-zero, you don't know what's for. Now you know what's for. It's not just some random concept that they come up with. Okay, but anyways, okay, let's look at part 3, very easy part. So guys, honestly, I all can aim for 4 out of 5 marks. Okay, I know it looks damn difficult, right? Okay, but it's 4 out of 5 marks in these 3 parts, which is honestly damn good, right? Okay, so for part 3, can you all tell me what's this reaction called? Okay, what's this reaction? Oops. Okay, they say it's SN1, right? Okay, so this one should be quite obvious. SN1 nucleus up, and just draw your 2 steps. Okay, so again, it's shit that you see in the notes. Alright, so I have this. And the first step is just the slow step where you only have 1 reactor. No nucleophile here yet. I need to see the partial charges and then the bond breaking. And that's how you form your carbocation. Like that. Second step, just attack the nucleophile to the carbocation and finish. Lone pair on OH minus, attack the carbon. Okay, so I really make sure that my arrow is not unambiguous. I attack the carbon. Can you see that? And when I attack the carbon, that's how I can get my fast step. And finish. This is honestly a freaking easy mechanism. SN1 is 10 times easier than SN2. That's for sure. Okay? Sorry? Where got HP? I'm confused. No, it's just a neutral sum. Yeah. Okay, you end up getting, oh, sorry. Okay, you will get a BR minus here, but no HBr. Alright. Okay, exam is a game where you're trying to get as much marks as possible. So you see part 2, right? You don't really see it's worth your time. Then you move on to part 3. You can get 4 out of 5 marks. Great, perfect. Okay, let's move on. Okay, so from here, I want you guys to finish up the rest of this pattern. Everything else. Everything else is very easy because it's all stuff we have seen in our notes. Only part 2 is difficult. Okay, so go and try. It's about 9 marks for the rest of the question. I know it's a bit long. I'm just going to give you guys 10 minutes. Okay, I'm not going to multiply by 1.5 here because there's nothing too difficult about some questions. Okay. Part 4 parts 5, 6, 7. 7 minutes left. Do the questions that you're very confident with. It's all about scoring as much marks. Okay, we're about less than 5 minutes left, 4 minutes. 3 minutes and 30 seconds left. Okay, and time's up. All right. Okay, if you can do this in 10 minutes, I think generally most of you guys can cover 10 minutes are pretty good. Okay, but the maximum amount of time allocated should be 13.5 minutes. Don't stretch it though, because I feel that 10 minutes is more appropriate. So whatever time that I give you guys, right, I feel that it's something that you should work towards. Okay, try not to get too comfortable with the amount of time you're allocated. Okay, always must have like buffer time lah, right? Okay, but anyways, you'll take a look first at part 4. Part 4 is a simple answer. We've gone through this before and they're very generous to give you 2 marks. Okay, keywords, trigonal planar carbocation. Okay, you can attack with equal probability on both sides. Basically mixture. Enough for 2 marks. Okay, they're very generous here. Your school may not be as generous nowadays. Okay, this one may only give 1 mark in A levels. Okay. For part 5, rate equation is just this, okay, because once again, it is an SN1 nucleosub. You should only have 1 overall order. Overall order is what? 1 item in the rate equation. Okay, how do you calculate the rate constant? That's the question. How to calculate? Any idea? Okay, take note. Now you can calculate the rate constant by subbing in the rate and subbing in the concentration. But do I have the rate of this equation? No, right? I don't have the rate of reaction. So I can only use the other method, which is half-life. Half-life equals the ln 2 over K. But I just want to recap one thing, right? This K is a very specific K. You can only use this K if the overall order is first order, yes. Only if overall order is 1, then you can sub in the value of K. Now the keyword here is overall order. So in this question, is the overall order 1? Yes. Overall order is 1, you can take that value of K straight up to find half-life. So, in other words, I can just take ln 2 over the half-life, 277, 2.5 times 10 to the power minus 3. You can include the units inside as well, just in case. This is per second. Make sense? Now, I just want to recap one other idea of you guys, in case you forgot about your kinetics concepts. Okay? Now, what if the rate of the reaction was second order? So you have Rx and nucleophile. Guys, what will you do over here? How do we calculate the rate constant? If the overall order is not equals to 1, what should I do? Are we just stuck here? Now guys, if you look at the first part of the question, they did say that the nucleophile is 2 mole per dm cube. Rx is 0.05 mole per dm cube, which allows the nucleophile to be in, what's this? Large excess. So the reaction is pseudo 0 order, because now he doesn't affect the change in rate, right? So if this guy remains relatively constant, this guy is also a constant. We can lump them together to form K prime. So based on the conditions in the question, I can form K prime and Rx. Now guys, is now an overall first order reaction? Yes. Now this is overall first order. So I can basically find ln 2 over what? K? Should be K prime. Because you must use this K prime because it's overall first order. So it's ln 2 over K times nucleophile. So in situations like this, right, the item that is in large excess, as you can see over here, will actually affect the half-life. So if I multiply the nucleophile's concentration by 2, my half-life will become faster, right? By 2 times. Okay, so this is another scenario that can possibly come out as well. Can see that? All that kinetics concepts are. Now, if you're going to revise your kinetics, I really suggest you all do it this way. Okay, kinetics is all about 2 things. The first branch of kinetics is all about measuring rate. Again, kinetics is all about understanding whether the reaction is fast or slow. For sometimes you want the reaction to be fast, sometimes you want the reaction to be slow. Okay, you want reaction to be fast, like Panadol. You eat Panadol, you want the reaction to be very fast, so your headache disappears in 5 minutes. Okay, but you want reactions to be slow because, like, let's say you are in operation, anesthesia. You want to make sure that the reaction is slow. You don't wake up halfway throughout the operation. So we have, if you want to change the rate, there's another way as well. You can influence rate. You can make rate slow or you can make rate fast. Now, guys, this is the easy part of kinetics where it's tested in part 6. Okay, when you increase temperature, it will definitely increase rate. So that's one possible reason why operations are done in a cold, right? Okay, so as well as measuring rate is all about your half-life and the more technical shit, right? Okay, all the experimental techniques. Okay, your pseudo zero, all that whatnot. So guys, when you study influencing rate, right, it's all about explanation. What happens when you increase temperature? Guys, how will you explain this? When temperature increases, what else also increases? Okay, temperature must affect what? The kinetic energy of the molecules, right? Now, if the kinetic energy increases, then what's the next thing to explain? Okay, it's been a while, so you probably forgot the keywords. But take note, now there's a higher proportion of molecules that have what? A higher proportion of molecules that have kinetic energy more than or equal to the activation energy. This is the classic explanation. If more molecules have higher energy than the activation energy, that means there will be a higher frequency of effective collisions. Now take note, when you influence rate, it's all about collision theory. Collision theory is all about your effective collisions and whatnot. So I need to see the word frequency of effective collisions, because the idea is directly proportional to rate. If there's higher frequency of effective collisions, your rate will be higher as well. That's your full explanation. Okay? Now they're nice to give you 2 marks over here. Okay, but sometimes it will be 3 marks. If it's a 3-mark question, what do you need to draw also? Do you remember? What's that diagram called? Okay, the Boltzmann distribution diagram. Okay, that one, right, is if it's a 3-mark question, you need to draw this one, then your activation energy and whatnot. Okay, can you remember? Yeah, so now we're going to revise 3 marks over here. Part 2, we literally did it just now, same exact question, easy. Okay, finish. And after we're done with this, then I will explain our next part, which is the final part of this question. Now, the final part is one of those like 1-mark questions that are a little bit harder to get. So, by right, if you guys do everything correctly, right, everything's all content, except for part 2 and the last part, you can get only 2 marks deducted, which is excellent, guys. That is your road to getting an A, right? Yes. Increase. Higher temperature. Wait, sorry. Oh, this one. Sorry. Oh, yeah. Decrease, right? Because the bond is stronger. Stronger, harder to break, so it takes longer. Rate is lower. Okay. Takes longer means rate is slower. Slow and fast. Think of slow and fast. You take longer means it's slower, Slower means lower rate. And faster means higher rate. You see that? Rate is the speed of a reaction. Slow speed and fast speed. You see that? Although I think I'm a bit confused. Faster means rate is higher. Slower means rate is slower. Can it? Yeah, okay? Can? Okay, as I said, only part 2 and part 7, right, are questions that you can afford to get wrong, because these are harder to explain. So if you can get the rest correct, it's 12 out of 14 marks. That's honestly freaking good, guys. Okay, so the rest can work on it. Okay, so let me just explain the last part for the sake of the question. Okay, so let me just write down a few things. They said water is more polar than ethanol. Okay. Then what did they say next? If they replace the aqueous NaOH, which is obviously water, okay, with ethanolic NaOH, reaction becomes slower. Okay, so this is faster SN1. This is a slower SN1. That's one of the questions to us so far. Okay, let's try to break this down. Guys, what's happening? They asked us to refer to this mechanism as well, right? Now, there's just one thing I need you guys to get correct. Okay, the answer itself, if you get wrong, I honestly don't really care. Okay? I want to see your approach to answer questions like this. They replace the solvent, agree? When they replace the solvent, the rate is affected. Okay, I say again, replace solvent, rate is affected. Okay, so what's happening? Guys, in SN1 reactions, okay, how and what affects the rate? Okay, I ask you guys this question, you tell me whether it's correct or wrong. Okay, I change the solvent and it affects NaOH. That's why the rate is affected. Is this correct? You see this, because the solvent is directly tied to NaOH, right? A lot of students will possibly tell me that the solvent will affect NaOH. It makes sense, right? Because it's in NaOH, correct? But can we discuss NaOH in this question? Why not? Guys, this is an SN1 reaction, right? SN1, as you already saw, the rate is only affected by what? The rate is only affected by Rx. Can you see that? So, if there's something to do with rate, it must affect Rx and not NaOH. This is the trap that the examiners have set for you. They say NaOH equals an NaOH ethanol link. Then they purposely want you all to get baited into explaining NaOH. But no, cannot explain NaOH. Because it doesn't affect the rate. What must you tell me instead? What does it affect, guys? If the rate is affected, that means it is affected by Rx. So this is the correct path. You change the solvent, and that solvent will affect the Rx, not the NaOH. So do not discuss anything about NaOH. If not, the moment you write NaOH, okay, exact the whole thing wrong already. Not relevant because it doesn't affect the rate in SN1. Can see that? Okay, this one really highlights your ability to see what is the rate equation. As for the rest, let me just explain to you guys now. All right, you all see this. Look at the mechanism because they ask you to look at. Okay, which step is more relevant? Which step do we look at? Okay, do we care about the second step? Does it affect the rate? No, it's a fast step. Erase. Okay, so if you erase this already, how do you explain? Look at the first step. Okay, possibly what could happen in this question is this. Right? You change the solvent and then it must affect this thing over here, right? You notice the rate is only dependent on how fast this bond breaks. So one possible reason is this. Ethanol is less polar than water, right? Okay, so if you have a less polar solvent, what could possibly happen is that this bond is not as polarized. Okay, I show you. Water is more polar. If it's more polar, means the CBr bond, right? The charge is very polarized, very big. If it's very polarized, that means this bond breaks very easily. Okay, on the other hand, if you use ethanol, right? Ethanol is less polar. So another possible reason is less polar means the CBr bond, the charges have to be bigger or smaller? Smaller, like a lot smaller, not as polarized. So is it easier or harder to break? It's a lot harder to break this bond, right? You see that? That's one possible reason. The answer talks about the stability of the carbocation, which I don't feel is a very good answer. Because this one doesn't talk about what's actually happening in the slow step. It talks about what's after the slow step. But it makes sense to a certain extent. It's just harder for you to think of it. Okay, so this is my preferred answer. So let me just write it down. Okay. Again, this part is really up to your own creativity and imagination already. Okay, what I'm more concerned with is whether you all can go on the right path in the first place. Okay, so you all can say something like this. Ethanol is less polar than water. Okay, thus it polarizes the electron cloud of CBr to a smaller extent. So now I'm just polishing my answer. The idea is there. Since it's polarized to a smaller extent, you can tell me that now CBr bond is harder to break in the slow step. That's why it's slower. Okay, that's one possible reason. Okay. So yeah, usually all these 1 mark questions, I say that you can afford to get it wrong, right? But I'm not saying that you must get it wrong by skipping. Okay, no, but sometimes you must try. Sometimes you never know you can get that 1 mark. You can surprise yourself. That 1 mark can save you. All right. And yeah, I spent so much time explaining only part 2 and part 7. On the other hand, the rest is everything you know already. Because I see you can actually score. It is very possible. Okay, the whole paper were questions like this, then I can understand why you're not doing well. But honestly, you study, right? You understand all the basic concepts. You can really do well for this freaking question. 12 out of 14. Go and aim for that. 12 out of 14. Okay, any questions so far? Okay, if there are no issues, okay, we all need a break. Because I try to want to do try to do more. We want to do a bit more questions. Okay, now okay we just do another question first, then maybe after this question we see if we got time we can take a break. Okay, we all now turn over to question 7. Okay, we do a organic question. Okay, question 7 is only made out of 4 parts, and honestly speaking, right, very honestly speaking, if you know your reactions well, you can aim for 6 out of 7 marks, I'd say first. Okay, and you will know which is that 1 mark that's hard to get. Right, later when you all see the question yourself. Okay, try the whole thing. For 7 marks, I'll give you guys 10 minutes. Okay. Some marks are quite easy to score, not gonna lie. Yeah, I know there might be a carbonyl functional group, but we have actually learned this reaction in the alcohols topic. So I won't ask you guys anything that we haven't learned yet. Like carbonyls haven't teach you all yet, never mind. Some of these reactions we actually see before. 5 minutes left. Regions and conditions are the one can score marks. Okay, part 1 to part 3. Let's get the marks here. Part 4 is the hard one. Yeah, and do up your cheat sheet soon so your reagents and conditions can remember. Right? You're gonna challenge yourself, you'll have a bit of fun, right? It's the last question. Maybe just give you another 2 more minutes, okay, because at some point you might be stuck, right? Okay, 1 more minute. Right. You might end up getting sucked into part 4. Then you might end up spending too much time in part 4. Because it's one of those questions where you think you can get it right, but you're not that confident you can get it. So you end up spending more and more time, and then you start wasting a lot of time for part 4. Okay, but you need to know when to move on also. So let me just go through the patterns now. Okay, guys, come, let's just go through this. Right, I later go through with you how to do part 4 together. Okay, but for now, look at the rest. Okay, part 1, they're asking as simple as type of reaction. Okay, I'm just going to list all the way from 1, 2, and 3. What's the reaction in number 1 called? Okay, it's actually, we have learned before, electro sub. Now, remember, electrophilic sub means the reaction is happening on which functional group? Benzene. So here you can already see the reaction happens by substituting the H on benzene. So it's 100% going to be electro sub. Now, let's recall why is this electro sub? Guys, when you look at electro sub of a normal benzene, right? How many possible reagents are there? What are the possible reagents? There are 3. Can you remember? NO2 plus. What else? What else can you sub in? Halogens, right? Or you can substitute alkyl groups. Okay. For this, I actually explain what this as one of the examples. I've actually told some of you guys the example of this reaction happening. Out of these 3 that we have learned in our syllabus, which one does this fall under? Okay, it falls under alkyl group, nothing else, right? It can't be halogen or NO2. Okay, so what I'm more interested in is when you're studying alkylation, I need you guys to include this portion here in your cheat sheet. So how does this work? Now remember, if let's just say you want to substitute a CH3, this is the product, I need you all to include 2 other columns in your cheat sheet. Number 1, what's the electrophile and then what's the reagent actually used? Like if I ask you all, right, if you substitute CH3, what's the electrophile that was attacked? Okay, all you need to do is to put a plus on the reactant, right? Oh, sorry, on the substituent. So this is CH3 plus. If this is CH3 plus, I mean you can't generate the electrophile, you can't just introduce the electrophile straight away, right? You have to introduce a reagent which will then generate this electrophile. So what's the reagent here called? It's actually CH3 Cl. Remember, you just need to place a halogen there, right? And then the Cl will eventually leave to form this stronger electrophile. Now we just do more practices. So if we were to take a look at this reaction instead, guys, can someone tell me what's the electrophile here? If this was the product, what was the electrophile that was used? Good. Okay, CH3, CH2, or just a line with a positive charge over here, right? CH3, CH2. So what was the original reagent? Change the plus to a Cl. Guys, this is a pattern. You just need to follow this pattern for whatever structures that are thrown at you. Okay, you get something as difficult as this. Guys, that was the electrophile here called. How many carbons are there in the electrophile? 1, 2, 3, 4. So out of the 4, right? Where's the positive charge at? You can already see by now that the positive charge must be on the carbon that's attached to the benzene. Then from there, what's the original reagent like? Just go and draw this guy, change it to a Cl. That's it. Now all I'm going to do now, right, is to introduce this particular question into our situation. Okay, in our list of different electrophiles, right, guys, how do I get the electrophile here? What should I do? Add a plus charge to the carbon containing the double bond O. And then from there, what's the original reagent? Let's put a Cl there. Guys, what is this functional group called? You remember? We learned this recently. This is your acyl chloride. So honestly, they've done nothing special here except for add a stupid double bond O. And you're just doing the same thing as before. I need to see this in your cheat sheet because I need you all to recognize that alkylation can happen for any number of carbons. All you need to know what to do, right, is to derive what the original reagent is like. This is the step-by-step procedure that you should follow. If your cheat sheet only has stuff in the notes, right, I'm sorry, your cheat sheet is not going to be useful because the notes itself is not enough. These are the things that I give you guys in the notes. I need you all to include it in your cheat sheet because that's what is actually useful. Okay, so in other words, guys, might as well just go over the reagents and conditions as well. I just need to place this guy inside. What else? Remember for benzene electrosub, what else do you need to put? It's quite an intense reaction. So you also need to put in your AlCl3 catalyst. Can you tell me what's the conditions? Room temperature, warm or heat. Here should be room temperature. Why? Do you notice here this is not a normal benzene that you just substituted on? This benzene has an alkyl group. An alkyl group is electron donating. If you donate electrons to the benzene, benzene becomes more electron rich. If you're more electron rich, that means you're more reactive or less reactive? More reactive, right? If you're more reactive, do you require stronger or milder conditions to react? Milder. That's why room temperature is actually enough for this reaction to occur. Can see that now? So tricky reagents and conditions. But we just move on to the next one now. Second one, what's the reaction here called? The reaction is? What's this? Okay, this is reduction. Now remember, just recognize the functional groups. This is a ketone functional group that we have actually, you should know this functional group. I know we haven't learned the specific reactions yet, but we do know ketone comes from a secondary alcohol. So if you reverse the reaction, it's just reduction, right? So for reduction, can you tell me what reducing agent you need to use? I actually told you all one already. What is it? Can you remember the reducing agent? Lithium, aluminium, hydride in dry ether. Finish. That's the answer. Moving on to the third reaction, guys. What's this reaction called? This is? What's this? No, not electrosub. Remember, electrosub is only if the reaction is happening on the hydrogen on benzene. But this is happening on the normal halogenol alkane. Oh, sorry, happening on the alcohol. Alcohol substitute to Cl is nucleosub. You know, we have learned this in alcohols recently. All you need to do over here is to just add PCl5 at room temperature. Finish. Now, guys, is that SM1 or SM2 in this case? Is that SM1 or SM2? Okay, as I mentioned, SM1 and SM2 is for which functional group? SM1 and SM2 is for which functional group? Halogenal alkanes. In this case, I'm substituting an alcohol. Alcohol don't have SM1 or SM2. Okay, Ken? So yeah, with these, you can get the first 2 marks. First 4 marks already. First 2 parts is 4 marks. Which is pretty good already, 4 out of 7, but we can go higher. Okay, guys, any questions so far? Now, you don't have, let's look at part 3. Part 3 is a good question. Let's start it. Okay, they are taking distinguishing tests to a next level. Because normally, guys, distinguishing tests, they ask you to distinguish between, okay, let's just call this X and call this Y. How do you distinguish between X and Y? The shit is very easy. But here's a bit harder because can you highlight the words? How do you have a distinguishing test if the reaction is complete? Step 3 is complete. How will you have a test for this? Guys, can we understand what this means first? What does it mean for the reaction to be complete? Good. Okay. The reaction complete means no more compound X and only have what? Compound Y. Make sense? Okay, but we look at it even more carefully. This question is a bit tricky. The word to test if the reaction is complete. Now, guys, to test if the reaction is complete, can we test X? Will there be any positive observation for X? No. Instead, you will have a negative observation, right? For X. Because there's no more X. But if you choose to test for Y, then there will be a what observation? Positive observation. But can you think a little bit carefully here? Are we able to test for Y? Does that show necessarily that the reaction is complete? No. What am I talking about? Imagine you started off with 5 moles of X and 0 moles of Y, correct? Now, when the reaction is complete, what should you have? How many moles of X? And 5, right? That's called a complete reaction. But halfway through the reaction, you might have 3 of X and 2 of Y. Does this give you a positive observation for Y? Yes, still, right? Does that mean the reaction is complete? No. So you cannot actually use this observation. But what is more conclusive, guys? What is more conclusive? Okay. Now, halfway through the reaction, does X give a positive observation? Yes. When do you only get a negative observation? If the reaction has 0x. And 0x definitely means the reaction is complete. So only this path works. So guys, in other words, usually distinguishing test, you can choose either to distinguish this guy or this guy. But in this question, you can only distinguish X. Okay, so what are some possible ways? Look at the functional group. What can we do here? Secondary alcohol. What can secondary alcohol that Cl cannot undergo? Okay, first possible answer. Now go and know your reactions well. You can oxidize the alcohol. Because Cl cannot oxidize what, right? Can see that? Now guys, if you write KMnO4 here, it's wrong. Can someone tell me why is this wrong? So, secondary alcohol just oxidize to ketone, it doesn't oxidize to anything else. Doesn't matter if it's strong or weak. What's the reason here actually? If you use KMnO4 for these two guys, there's one reaction that both of them can undergo. Side chain oxidation. Take note, guys, side chain oxidation need you use KMnO4. Both of them have side chain, so both will oxidize. That means it's not good already. K2Cl2O7 cannot undergo side chain, so you will only oxidize the secondary alcohol. Now, can I ask you, what's the observation in this question? If you choose to use dichromate, the orange, does it turn to green? No. As we already mentioned, it must have a negative observation. If you have no more X, so you can phrase your answer this way. If the reaction is complete, you shouldn't have any X, right? So the orange dichromate should remain orange. Does that make sense? So tricky, when they ask for testing if the reaction is complete, the only way is to see if there's no more reactant, not about how much products you have. Okay, no more reactant must be negative observation. Okay, there's another possible answer here, guys. Look at secondary alcohol. What other reactions can we have? What other reactions? Okay, good. Iodoform test. Iodoform test, I know now you all just learn only, but as long as you can spot the methyl alcohol. Spotting a methyl alcohol allows you to undergo iodoform test. So in this case, guys, can you tell me what's the observation like? If the reaction is complete, then what do you see? Have yellow or no yellow? No yellow. Because if you have, that means this one will have yellow. Okay, so no yellow. There's a third answer as well. Also with regards to alcohol reactions, what is it? Okay, this one you need to know your alcohol reactions well. I remember telling you guys there are 6 alcohol reactions, right? Not condensation. Condensation, yes, can happen, but there's no observation. The first reaction was redox. The first reaction that we learned was redox. In other words, if you add sodium at room temperature, guys, can you tell me what's the observation? If the reaction is complete, then what? Negative observation. So remember, if you add sodium, what do you see? Acid plus metal give you what? Okay, effervescence, right? Now, if the reaction is complete, then have effervescence or don't have? No. No effervescence of H2. So you just have to think in perspective, right, of how many alcohol reactions you have. I have a lot. 6 of them. First one was acid metal. Acid metal is here. There's an observation, can use. Second one was condensation. Condensation has no observation, cannot use. Third one, nucleosub. Nucleosub in this case can also, but okay, the observation not very clear. Okay. Number 4, dehydration. Dehydration, no observation. 5 is oxidation. 6 is iodoform test. Okay. So there's actually one more reaction here, but we stick to this. As long as you got 3, I think it's good enough. Okay, you just need to choose one. Any questions so far? No, so that's why it's 2 marks. It's a bit difficult. Okay, so think of this. Okay, come. Let's move on to the last one. I'm going to show you guys how to do this kind of questions because you will see this. Okay, in future, maybe the whole question is dependent on this kind of question type. Okay, you will see it's not just a one-off 1 mark question. Okay, guys, what is this kind of question called? You have never learned what a Greek nut reagent is. You have never learned how this reaction works. So what is it called? Okay, take note. This is a, we write here, pattern recognition question. A pattern recognition question means they give you something you've never seen before. All you need to do is to identify patterns and then transfer that knowledge, right? Transfer that pattern over to whatever they are asking you for. Okay, take note, this is a difficult question type. We need to know how to do this kind of questions, how to approach them. Sometimes at some point I can only tell you how to do it, right? But then patterns are very inherent. So if you can identify patterns well, right, these kind of questions are very good for you. Like personally, for me, I'm very good at identifying patterns. Okay, but of course, to some extent, right, you all need to be able to see yourself. So you need to train yourself to see. Okay, guys, here look at this reaction here. Grignard reagent, right? I will tell you more in the next chapter when we do carbonyl compounds. Grignard is a very common pattern recognition. So it's so commonly tested to the point, right, where I will consider now Grignard to be part of the syllabus. Okay, honestly. Okay, we will learn how to draw Grignard reagent. Your school may not teach you. Okay, but anyways, pattern recognition, guys, I just need you to tell me literally from here to here what happened. That's all you need to tell me. What changes do you see? You just need to list down. What happened to the double bond O? Okay, yeah, write it down. Yeah, okay, so the double bond O become OH. Okay, so write something like that. No, this one not, this is for your own sake. So write short and concise. Okay, guys, next. The second one there. Anything else that you see? Anything you observe from here to here? You can pretty much ignore the intermediate region. Just stare at this guy and stare at this guy. Start at end. Don't care about the middle. Okay, what else do you notice? Okay, the R, right, is attached to this guy here, right? Okay, just put that in. R is attached to carbon. Yeah, something like that. That's all that happened. Nothing else happened. Right, guys? That's literally it. Next lesson, next time when you learn carbonyls, next lesson, when you learn nucleophilic addition mechanism, this will be a lot easier. Okay, but this one, since you all don't know, right, is to train your patterns. Okay, guys, where did the R come from? Okay, good. Go and circle him out. The R come from here. Go and draw shit inside your diagram. Like, go and draw an arrow just attaching it there. When you all draw things, right, it really helps. Okay, then the next thing is the OH. Double bond O turn into OH. Go and circle that shit and just draw an arrow. Yeah, okay, make your paper messy. If your paper is not messy, that means you're doing something wrong. Okay? Okay, something like that. Okay, then we just need to repeat the same thing for whatever you see up here, right? Okay. Can get me so far? We study this pattern. This is our results from our study. Come, look at this again. This shit, right, happens here. So contextualize your question. He already said that this guy is a Grignard reagent. So can I ask you, the reagent Z is the what? You draw parallels. Reagent Z is the what? This one, right? This one. Okay, we can call this the carbonyl. That one, literally. Can? Okay, next. Okay, now that you know who is who, we transpose the pattern across. So how? Okay, who's the R group? Where's the R group? Over here. You can see it. The R is attached to MgCl. So find your MgCl. This entire part is your R group. You can see that. Circle. It must be messy. If it's not messy, you're not doing things right. Okay, if it's R, okay, come. Then we come back here. Okay, we do not know what this guy is, so this one a bit hard yet. A bit hard for now. So we have to study the end product and then work our way backwards. So that's how I start. Okay, guys, study the end product. Okay, and then read your observations. Look at the first one, guys. Double bond O become OH. Where's the OH? You can see it. Where's the OH? It's right here, right? So initially this OH was what? If you want to reverse back to compound set, double bond O, just put here first to remind yourself. Okay? Then what's next? Where's the R group? R attached to C, then you remove the R. Right? Can you see that R is just this part? Same shit here. Can you see that? So remove the R. Like literally like remove the R like this. The whole thing gone. So where's reagent Z? Reagent Z is right here, right? Can you see that? Oh yeah, sure. Thank you. Okay, can you see this? The OH turn back to C double bond O. C double bond O, double bond O. What's the answer? CO2. C double bond O. Then the OH turn back to C double bond O. I know this stuff because it's not a carbonyl. Okay, so it's not a carbonyl in this case. It's a bit tricky. Answer CO2. Now, if you all still cannot see it, tell me right now, then I'll just draw out the forward reaction. Okay? You all can't see it possibly because you're going backwards. Come, I draw forwards for you all. Remember the pattern I erase first. Come. Okay? RMgCl. R is this shit here, the big ass thing. They bond to MgCl, right? Then this one is carbon dioxide, CO2. Okay? Okay, you're not convinced, you look at this, Okay, I skip the middle, I don't care about this guy. Go to the end. Okay, what happened to the double bond O? Double bond O is your number one change, right? Turn into OH. Correct? Okay, draw here first though. Okay, I'm not doing shit, I'm just drawing it out only. Can? What's next? What's the second thing that happened? Okay, go and read your list. You forget, you read again. Your R, which is here, attached to this carbon. So you see this carbon here, just going to draw that circled shit out. And that's pretty much it. This has nothing to do with chemistry, this has to do with patterns. And is that the answer? Yes. Sometimes you can work forwards also. Work forwards, right? Maybe you have your answer, maybe your answer is slightly off, but you work forwards to see. Okay. Sometimes if you work forwards with your wrong answer, right, you might actually end up troubleshooting that answer and then you can get it correct. You never know. Okay, so that's how you deal with patterns. I know for 1 mark it's tough and it's not worth it. Okay, but I will make sure you all know how to do this because some questions, right, are purely based on patterns. Okay, and you know, eventually when you all get good at this, now don't just skip. Okay, this one must go and actually try. Don't care about the 1 mark, 2 mark, whatever. Okay, now you must make sure you know. You train yourself such that eventually in the exam, boom, you can see at the first glance. Okay, this is tough. It's hard to see at first glance. I can't see this on first glance. I need to do shit like this, where I list down what happened, and then I just draw here, draw there. Okay, draw your arrows. I can't see straight away. Okay, so I don't expect you guys to see straight away also. Okay, anyways, any questions? If not, that's it for today. Yeah, time flies when you're having fun. Okay, so yeah, that's it for today. I'll see you guys next week. Right? Remember, the following week is March holidays. There will be a time I need you guys to come down to do a mock paper free. Okay, can? Next week you start on carbon house.